Okay, so in this lecture, let us discuss the state reduction and assignment. We know that analysis of a sequential circuit, starts from circuit diagram, or you can call it a logic diagram. Okay, so you will start from the circuit diagram or a logic diagram and culminates in a state table or a state diagram. So this is what we typically do whenever we want to analyze a sequential circuit. Okay, on the other hand, when you want to do a design, also called synthesis. Okay, so whenever we want to design a sequential circuit, then it starts from a set of specifications. Set of specifications are given, and from that specifications we need to find out the logic diagram. The specifications are given by the customer or from the end user, and from that specification we need to find out the suitable logic diagram or something called a circuit diagram, whatever it is. So that is the design of an engineer. So he has to work out and find the suitable logic diagram. Now suppose for a given problem I have two sequential circuit. Let me call sequential circuit 1 and sequential circuit 2. So there are two sequential circuits and I am giving inputs and it produces corresponding outputs, let's say X and Y. This is A and B. Then here also I am giving the same A and B, and this guy also produces the same output X and Y. Okay, so that means what I am trying to say here is two sequential circuits may exhibit the same input output behavior. See, here the input is A and B, and here also A and B, and both of them producing the same output. Okay, but this sequential circuit 1 and 2 may have a different number of internal states in their state diagram. So it may have different internal states. That doesn't matter. They are not identical, but their behavior is identical. If you give 0, the corresponding output, let's say 0, and here also if you give 0, then it gives 0. If you give 1, it gives 0, and here also if you give 1, and here also it gives 0, something like that. Okay, so I have two sequential circuit. Their internal structure or internal circuit is different, but they are giving same output. Okay, so in this lecture, let us discuss certain properties of the sequential circuit that may simplify design by reducing the number of gates. For example, this circuit uses 10 gates, and this guy uses, let's say, 8 gates. Which one do you prefer? Obviously 8 gates. And this guy uses, let's say, 3 flip-flops, and this uses 5 flip-flops. But both of them giving same set of input output behavior. So obviously you will choose the second sequential circuit because it uses less number of gates and less number of flip-flops, and implies that the cost will be reduced. Therefore, somehow we need to reduce the number of states. If the number of states are reduced, then your cost will come down. Therefore, the main focus of this lecture is how one can reduce the number of states, because number of states essentially implies the cost of the circuit. If you reduce the number of states, then then automatically number of flip-flops will be reduced and the logic gates also will be reduced. So that is the prime purpose of this lecture. So how one can reduce the number of states from the given specification. See, set of specifications are given, in between you will find out the set of states, and from that set of states you should not put too many states. Somehow you need to reduce the number of states. So that's a simplification procedure. So that means reducing the number of gates and the number of flip-flops. In general, reducing the number of flip-flops reduce the cost of circuits. Reducing the number of flip-flops reduces the cost of the circuit. So that is the whole purpose of state reduction techniques. Now let's say state reduction. Let us discuss state reduction, how one can reduce a state. So the reduction in the number of flip-flops in a sequential circuit is referred to as the state reduction problem. So therefore, to reduce the number of states, we have an algorithm called a state reduction algorithm. State reduction algorithm. So I am going to discuss this algorithm without proof. So this state reduction algorithm reduces the number of states in a state table, but it doesn't mean that it is going to affect the internal and going to affect the external behavior, input output requirements. Okay, so the input and output behavior is not affected, but at the same time we are going to reduce the number of states. If number of states are reduced, then the number of flip-flops also reduced. We know that in case if I have m flip-flops, then how many states do I have? 2 power m states. Therefore, a state reduction in the number of states may or may not result in a state reduction in the number of flip-flops. See, for example, I have a set of specifications. For this specification, if I start to design, I may end up with 9 states. For 9 states, I need to use 4 flip-flops. Why? Because how do you represent 9? In binary form 1 0 0 1. So for this 1 flip-flop, for this 0 1 flip-flop, and this guy 1 flip-flop, and this guy 1 flip-flop. So 1 2 3 4 flip-flops I need. On the other hand, somehow I apply this 9 states to state reduction algorithm. And then I may reduce to, let's say, 7 states. Now maximum I have 7 states. With this 7 states, then I need only 3 bits, because 7 is represented by 1 1 1. I don't want 4 flip-flops. So you reduce the cost of 1 flip-flop. So that is the purpose of your state reduction algorithm. Therefore, whenever you reduce the number of states in your state table, then you are saving the money. Okay, so number of states reduces, then number of flip-flops reduces, therefore this implies cost also reduces. So this is one aspect. Sometimes it may not happen also. Sometimes if you try to do state reduction and you may not end up with 7, sometimes you may end up with 8, then again you are forced to use 4 flip-flops. Sometimes it may not help you also. Okay, so whenever you do the state reduction, then you will end up with a fewer flip-flops. Now let us discuss the state reduction procedure. So this state reduction procedure, let us try to understand with the help of an example. So I'm going to consider this state diagram. State reduction procedure. So consider this state diagram. Okay, let us start with a sequential circuit whose specification is given in the form of a diagram called a state diagram. So in this example, only input output sequences are input. See, this 0 is input and slash, and this one represents output, and this 0 is input and this 0 is output. Okay, so input slash output, that is a notation. Okay, don't get confused. Now I have how many states are there? 1 2 3 4 5 6 7 states are there. So let us try to see, let us try to reduce the number of states if possible. Now the internal states are A, B, C, D, E, F and G. Okay, so the states are marked inside the circles, and we are giving the letters, okay, to denote the states. And sometimes later on we will study binary counter. In the binary counter, the states are denoted by like this: 0 0 1, then 0 0 0, like this, then 0 1 0, then 0 1 1, like this, keep on goes. So there these internal values are important, but here in our design internal values are not important. Internal values are not important. What we want to consider is the input output behavior. We least bother about the internal states. That means we are trying to reduce the number of internal states. So somehow reduce this guy, reduce this guy, reduce that guy. That is our primary motto. But on the other hand, when you take some counters, binary counter and all, their internal states are important. So this is important point. Don't get confused. Later on we will discuss a counter called a binary counter. There the internal states are important. Internal states are important, but here it is not important. Okay, we want to get rid of some important some internal states. We want to get rid of some internal states or some states. Why? To save the money. So this is a given circuit diagram, sorry, state diagram. Okay, this is the given state diagram, and for this state diagram there are infinite number of sequences that may be applied to the circuit. See, this is my state diagram. I can represent like as a circuit diagram, and this is my input sequences, and here output sequences. So 1 0 1 1 0 1, like this I am giving. So like this I can apply infinite number of sequences. Okay, these sequences are applied to the sequential circuit, and each input sequence results in a unique output sequence. Okay, as an example, let us consider the sequence 0 1 0 1 0 1 1 0 1 0 0. Okay, and let us start from the state A. The state is here, this state. Let us start from the state A. Now let me use here only, so that with the respect to the figure I'll be able to explain nicely. So around the figure I need space. Okay, so 0 1 0 1 0 1 1 0 1 0 0, this is my input sequence. Now let me start from the initial state A. Okay, so initial state A, and each input of 0 or 1 produces an output of 0 or 1. Look at the state here. If you apply 0, then output is 0, right? And if you apply 1, the output is 0, right? For 0 input, 0 output, and the state remains in the state A, and 1 input and 0 is out, input is 1 and output is 0, but the state moves to state B. Okay, so if we apply 0 to the sequential circuit, the output will be 0 or 1. If we apply 1, then the output will be 0 or 1, and it may go to the next state or may not. Therefore, the input causes the circuit to go to the next state. The input causes the circuit to go to the next state. I mean, it will go to the next state or it stays in the same state. Next state or to stay in the same state. Anything can happen. Okay, so therefore we obtain the output and the state sequence for the given input sequence. Okay, so whenever you apply the input, then we will get the output and also state. Now let us start with the circuit diagram with the initial state A and an input is 0. Okay, so let me draw a, let me try to find out the sequences with the present state A and an input of 1. So look at the state diagram. Input of first let us start with the 0. Input is 0. Now what is going to happen? What is output? Output also 0. Look, if you look at the state diagram, you will be able to write down. Look at here. Input is 0 and output also 0, and the state stays in the same state. It will not move. And now if you apply 1, input is 1 and output is, look at here, output is 0, but the state is moved from A to B. Now in the B, if you apply 0, input is 0, output is 0. Now what happens? It moves from state B to C. And in the state C, again you apply 1. Look at here, apply 1 and the output is 0, but you are moving from state C to state D. Like this you can keep on fill it up. Okay, so if you continue this process, we find a complete sequences. Okay, in each column we have a present state. The top one is present state input value and output value. Okay, so it is important to realize that in the circuit the states themselves are of secondary importance, because we are interested only in the, as I said, output sequences caused by the input sequences. Okay, our motto is somehow we need to get rid of some internal states so that we can save the money and we can reduce the number of gates and number of flip-flops. Okay, so let us assume that, as I said, given a sequential circuit which has this sequential circuit has 7 states. Somehow you reduce a new sequential circuit with a number of states less than 7. Then this is good for us, right? So you are saving the money and you are making the circuit very simple, and in turn you are saving the space also in the chip. Okay, so these are the two. Let's say this is circuit 1 and this is circuit 2, and we wish to compare the given circuit with our new circuit. This is my new circuit and this is my given circuit. If identical input sequences are applied to this circuit 1 and circuit 2 and both of them produces identical outputs for all input sequences, then the two circuits are said to be equivalent. So obviously one should choose the circuit which uses the less number of states. Okay, these two circuits are equivalent as far as the input and output is concerned, not with the internal structure or internally how the gates are connected. We least bother about it. As an end user, I don't worry, okay, what is there inside. I worried only about the input and output behavior. Okay, if you buy a product, you are not going to look into how the products are constructed, how the products are made. The only thing is you apply certain input and certain output, that's it. Suppose if you buy a car, you least bother, okay, what is there inside the machine or whatever it is. Of course you need to look into that, but as an end user, okay, how comfortable the car is and how, okay, the stability of the car on the road and fuel efficiency and body build quality, these are the things you generally look into that. But how internally the drive mechanisms are there and fuel injection, all those things, you don't worry about that. The only thing is you need best out of from that, that's it. Okay, suppose if you apply 0 0 0 4 zeros as your input sequence, then you must apply all possible combinations. Okay, don't simply apply one sequence and both of them giving identical output like that, and don't say like that. So you apply all possible input sequences, start from 0 0 0 1 0 0 1 0 and give up to 1 1 1. For each input sequence it produces certain output sequence. Both of them should be identical. Okay, you must apply all the possible combinations to both circuits and verify the output whether they are identical. If they, then you say the two circuits are equivalent. Therefore one may be replaced by the other. I don't use the 7 state, I will use with a less number of states. So this is the problem of state reduction. So the problem of state reduction is to find ways of reducing the number of states in a sequential circuit without altering the input output relationship. So that one has to be remembered. Now we need to proceed to reduce the number of states for this given example. First we need the state table. So because once you have the state table, then it is more convenient to apply the state reduction algorithm. With the state diagram it is little difficult. So let us apply the let us try to form the state table. So the state table is given here. 1 minute. Okay, so there are 3 set of columns and you have present state. Let me move 1 minute. I'll bring it close to the figure. Yeah, I think it's coming in one window. Oh fine, that's fine. Okay, maybe I'll reduce. Yes. Now if you take present state is 0 and input is 0, output is 1 second. Look at the state diagram now and state table simultaneously. So So instead of looking at the table, let me write down. Okay, that would be better to understand, easiest way to understand. Okay, so take the input present state A, and you go to the next state A. When will you go? When the input is x equal to 0, and you go to the next state B. When will you go? When x is 1. When the input is 0, what is output? Output is 0. If you look at that state table, this is 0. Similarly, when the input is 1, what is output? Output also 0. That's what you have filled it here. And the next state is B. From B, you look at the figure. For B, if you give input is 0, input is 0, then it goes to the state C. If the input is 1, x is 1, then it goes to state D. When it goes to the state D, what is the output? Output is 0. So you put 1 here and here 0. Like that you can keep on fill it up. Okay, so look at the state table construction is straightforward from the state diagram. For example, you take this state G. Where is G? G is here. Okay, from G to F we are moving. When the input is 1, when the input is 1, then the output is 1. See, input is 1, output is 1. Right? When the input is 0, output also 0. Input is 0, output also 0. Now when the input is 1, when the input is 1, it moves to F state. See, input is 1, it moves to F state. When the input is 0, it moves to A state, it goes to A. This is the state table. So from the state table, it is very easy to apply the algorithm. So that's why we constructed the state table. So the algorithm is explained without proof. So now, as I said, two states are said to be equivalent if each member of the set of inputs, they give exactly the same output. So then we say the two states are equivalent. Okay, and send the circuit to the same state or to an equivalent state. When the two states are equivalent, one of them can be removed without altering the input-output relationship. Now, if you go through the state table, you will come to know. Just to go through the table row by row, if you go through, okay, and just to go through the table row by row and apply this algorithm. Now we look for two present states that go to the same next state. See, this is my present state, and this is next state. These two are next states, and look at two rows such that the present state go to the same next state and have the same output for both the input. Output also should be same. For example, if you look at very carefully, take state E and G. For E, if you give input 0, it produces output 0 and it goes to state A. G also, if you give input 0, output is 0 and it goes to the same state A. And this is one possible input. What is the other possible input? E, give 1 as input and the output is 1. And take G, and the other possible input is 1 and the output is output is 1, and it goes to again same state A and A, isn't it? See, the input and output behavior is not changed, and the E state will go to A and G state will go to A. Similarly, here also E to A and E to A. Therefore, we have the same we have identical input output behavior, but the two different states will end up with the same state. Okay, so E and G both go to states A. This is E. I'm really sorry. This goes to F and this goes to F. When the input is 0, output is 0, it goes to A. When the input is 0, output is 0, it goes to A. And here also it goes to F and it goes to F. So therefore, one row can be erased. In this one row, see E and G, this one and this one, any one row you can delete. So let us start to delete from the last row. So I can delete this guy, I don't want, because this last row is identical with this row. So from this state table I can eliminate one row. That means we are reducing we have reduced one row. Okay, therefore states G and E are equivalent. So one of the states can be removed. Now that reduced is shown here. See, G is removed in this table. Okay, the row with the present state G is removed. That means state G is replaced by state E. Okay, so whenever G occurs, that G will be replaced by E, because both of them give the identical input output and next state behaviors. Now again look at this state table. Is there any possibility to reduce the number of states? Now if you look at properly, very keenly, then present state F okay, F now has next states E and F, and outputs 0 and 1. For this is for x equal to 0 and this is for x equal to 1, and this state is for x equal to 0 and this state for x equal to 1. Okay, now is there any other row which has this kind of relationship? If you look at row D, and here also E, both of them E, and this is F and this is F, and 0 0 1 1. Therefore D and F are identical. So any one row can be deleted now. Okay, so D, if we give 0, output is 0, it goes to E. The present state is F, give 0, output is 0, it goes to E. The present state is D, and give input 1 and the output is 1, it goes to F state. The present state is F, apply 1 and output is 1, and it goes again F state. So therefore D and E are identical. So you can replace F by D. Okay, so state F can be removed and replaced by D. Therefore the final state table is like this. So F is removed, so I left with A, B, C, D, E. So how many states do I have here? 5 states. So from 7 state we reduce it to 5 state. Now if you look at this reduced state table, it consists of only 5 states. And again, for these 5 states you can draw the state diagram. Okay. So present state is A. You circle with the A because the state is denoted by a circle, and inside you write it, and input is A, and you go to next state A only. So therefore input is 0, and what is output? Output is 0. Now when input is 1, you go to next state B. So input is 1, you go to the next state B. So this is my B. Okay, now you take B now. For B, input is 0, you go to C. So input is 0 and output is 0, but you move to state C. And when the input is 1, you move to the state D. Therefore input is 1 and the output is 0, but you move to the state D. So like that you can construct. Now take state C. State C, if the input is 0, you move back to state A. So input is 0 and output also 0. 0 cross 0, move back to A. Right? And in the state B, if the input is 1, you move to state D. Input is 1, you move to state D. When the input is 1, what is the output? You look at here. This one. Output is 0. In state D, if the input is 0, you move to E. So let's say this is E. From D to E, you move here. D to E. If the input is 1, this is for 1 and this is for 0. And you write down the corresponding output. This is 1 by 1 and this is 0 by 0. So rest of the things you can fill it up. So this is the reduced state diagram. So our state reduction algorithm has reduced the number of states from 7 to 5. Okay, so by judicious use of the table, it is possible to determine all pairs of equivalent states in the state table. Okay, so the sequential circuit of this example was reduced from 7 to 5 states. In general, reducing the number of states in a state table may result in a circuit with a less component. May result in a circuit with less component. Okay, why did I put may? Because we can't say 100%. Sometimes maybe, sometimes may not. But however, the fact that the state table has been reduced to fewer states, so we are saving the number of flip-flops, saving in the number of flip-flops or number of gates. So therefore in actual practice, the designers may skip this step because target devices are rich in resources. Now the next topic is state assignment. Till now we represented the state as A, then B, then C, then D, like this. But we can't use A, B, C, D in our actual implementation. So we need to assign the binary values to the states. So that is called state assignments. So there are different ways we can assign the values for the states. Okay, so at the end of the day we need to design a circuit, right? Design a sequential circuit with the physical components like gates, flip-flops, transistors, diodes, resistors, and so on and so forth. Okay, so in order to design a sequential circuit with the physical components, it is necessary to assign a unique code to each states, unique coded binary values. Okay, till now we used numbers, okay, some notations A, B, C, D, like that. But with that we can't design a circuit. We need, at the end of the day, your computer, your hardware works with ones and zeros. I can't go and tell the flip-flop or any other circuit with A, B, C, D and all. Okay. So we need to assign certain binary values. So it is necessary to assign unique coded binary values to the states. So let us say I have a circuit with m states. So therefore, for a circuit with m states, the codes must contain n bits. Now how this n and m are related? Your 2 power n must be greater than or equal to m. For example, I have 9 states. That means I can't go and tell the engineer to design with 3 flip-flops. I need 4 flip-flops because 2 power 4 is 16. 16 is greater than or equal to 9. Therefore, n must be 4. Therefore, this n and m are related in this fashion. So, m is 9 and n is 4. Okay. For example, if I have 3 bits, then we have 8 combinations. Starts from 0 0 0 0 1 0 1 0 0 1 1 and you go all the way up to 1 1 1, 3 ones. Okay, so with 3 bits we have 8 combinations. Therefore, with 3 bits it is possible to assign codes to 8 states. Here m is 8 and n is 3. And these states I cannot go and denote by A, B, C, D and all, because at the end of the day I need to design a circuit and we know that the circuit works only with the ones and zeros. That is the only reason we are using this binary representation. Okay, so these states must be denoted by a binary numbers 0 0 0 through 1 1 1. And of course there are different methods to assign the numbers. So here we have given 3 possible binary state assignments. One is binary, another one is gray code, and the last one is one hot method. So we must assign values to these 5 states, and the remaining states are unused. Okay, in case if you use this state table, how many states do we have? 7 states, and the 8th state is unused. So in digital circuit we have a privilege. What is the privilege? If anything is not used, we put don't care. We simply put don't care condition. Okay, if any combination is not used, simply we put don't care condition, and this don't care will help you to get a simpler expression when you simplify it. Okay, if you use this table, then we need 8 states and 1 state is unused. And in case if I use this table, then only I am going to use 5 states and the remaining 3 states are unused. Unused means don't care. Don't care means you will get a simpler expression. Look at from your K map. So in case if you take this K map, let's say this is 1 and remaining or don't cares like this, then what will happen? You'll get a simpler expression like this. If you combine these four guys and you get a simpler expression. In case if you don't have this don't care, then you will not get a simpler expression. That means you need more gates. For example, let us try to understand this a little bit more, because you may get doubt in this. Okay, now this is my like this. So let's say A, B, C, then what is going to happen? 0 0 0 1 1 1 1 0. So this is the expression is C, right? In case take the same thing, this is 0 as it is, this also 0, this is 1 and this is x, and this is 0 and this is x. What is going to happen now? You can't get a quad, you will get a pair. You will get this pair. Now A, B, C, then what is going to happen now? This is 0 0 0 1 1 1 1 0. So 0 1. So the expression, the Boolean expression for this is A bar, and then here C, A bar C. Therefore to implement this, I need one NOT gate. You give A and then C and then put an AND gate. So two additional gates are needed. Two additional gates are needed. Right, to implement this, to realize this. Because of this guy, okay, so you don't need any gates here. Here nothing is needed here, but here I need two extra combination circuit. Therefore, reducing the number of states not only reduces the number of flip-flops, but also reduces the number of gates in the combinational circuit. As I said, your sequential circuit consists of both flip-flops and gates, combinational circuits. Therefore, if you try to reduce the number of states, that means what? You have a lot of unused states. So unused states means don't care conditions. Whenever you have don't care conditions, then you are reducing the cost. You are getting the simpler Boolean expressions. So these are the advantages in reducing the states. Okay, so don't care conditions usually help in obtaining a simpler circuits. Okay, so it is more likely, but not certain, that the circuits with the 5 states will require fewer combinational gates than one with the 7 states. Sometimes it can happen, sometimes it may not. Now there are no 3 possible ways one can code the 5 states. So the simplest way to code 5 states is use the first 5 integers in binary counter order as shown below. See, you start from 0 0 0 0 1 0 1 0 0 1 1 1 0 0. So this is the simpler way to code it. Another similar assignment is the sorry, not this one. The state table is here. Where is it? Oh my god. Yeah, it's here. So 0 0 0 1 0 1 0 1 0 0 1 1 1 0 0. And another similar assignment is the gray code. Okay, and if you look at the gray code, if you move from the first row to the second row, only one bit is changed. And from second row to third row, again one bit is changed. See, 0 0 1 to 0 1 1, only one bit. Which bit is changed? The middle bit. 0 0 1 0 1 1, 1 to 1 no change, 0 to 0 no change, 1 to 0 to 1 change. So one bit is changed. Similarly, if you look at from the third row to fourth row, again one bit is changed. 0 to 0 no change, 1 to 1 no change, 1 to 0 yes, there is a single change. Again, if you look at from fourth row to fifth row, only one bit is changed. So that is the beauty of your gray code. Okay, going from one number to the next only one bit is changed. Okay, so only one bit in the code group changes when you move from one number to the next. And whenever you use a gray code, this makes it easier for the Boolean functions to be placed in the map for simplification. So this will give you simpler expressions. And another possible assignment is called the one-hot assignment. And this one-hot assignment is often used in the design of state machines. Something called state machines. Okay, the state machines are used to control data path units. Something called data path units, and this you will be studying in detail in your computer architecture and organization course. Okay, there people use the one hot assignment. But look at the beauty. Here we need 3 flip-flops, and here also in binary assignment also we need 3 flip-flops. But here how many? 3 plus 2, 5 flip-flops. Here the cost is little high. Instead of 3 we are using 5. Okay, this one hot assignment uses as many bits as there are states in the circuits. So if there are 5 states, I need 5 flip-flops. Okay, so that is a drawback of your one hot assignment. One hot assignment disadvantages. If you have 10 states, we need a 10 flip-flops. If you have 9 states, you need 9 flip-flops. Okay, that is a drawback. And how do you assign the codes? At any time only one bit is 1. At any given time only one bit is equal to 1, while all others are kept at 0. And this type of assignment uses one flip-flop per state. So therefore this one hot encoding usually leads to simpler decoding logic. So the advantage is, what is an advantage? Simpler decoding logic. So whenever you have some simpler decoding logic, then somehow you are ready to compromise, or ready to spend a little bit amount of money, because generally when you design a computer, or when you design any system or any communication circuit, then this encoding and decoding is a big process. So in that case, if you use this one hot assignment, then it leads to a simpler decoding logic for the next state and the output. So, and moreover, this one hot machines can be faster. Okay, these days people are ready to pay the money. Money is not a problem, but only thing is then the work has to be done little quickly. So that's why even if normal mobile phone costs us 10,000 rupees, but people are ready to spend 60,000 or 70,000, even 1 lakh also they are ready to spend to buy a mobile phone from Apple, right? Apple iPhones, because of their performance, speed, and screen resolution, and there are many things. Okay, so I'm not here to promote an Apple iPhone, but I'm just giving the comparison. And if you use simpler decoding logic, then that will be compensated by using less number of circuit in the decoder, and the silicon area required by the extra flip-flops can be offset by the area saved in using simpler decoding logic, because the decoding logic will be little higher and it needs a lot of gates and this and that. So instead of spending money on decoding logic, better spend money on the flip-flops and spend very less amount of money in the decoding logic. such that what happens, what is the benefit in this? You achieve faster circuit, faster operation. Spend money, spend on flip-flops, and less money or less cost on decoding logic. At the end of the day, both are compensated. See, for example, if you spend $10 and here, let's say here you are spending $8 and here you are going to spend $2. But on the other hand, what happens? This is for one shot. If you use binary and here you use 5 flip-flops, let us take 5 flip-flops and you spend $10 and $2 for decoding. If you use binary, then you are going to use only 3 flip-flops. 3 flip-flop means, let's say, $6. And here for decoding logic, you will end up with $6 for decoding. So totally again, if you look at $12, but speed is low here. But here speed is high. So that is a beauty. Somehow you compensate here or there. And and this one is okay, for state A we denoted by 0 0 0, state B we denoted by 0 0 1. And look at this state table, this zero is, this state A is 0 0 0 and this also 0 0 0 and B is 0 0 1. And here B is 0 0 1, C is 0 1 0, D is 0 1 1, E is 1 0 0. Is that right? And this A is 0 0 0 0, E is 1 0 0, and A is 0 0 0, and C is 0 1 0, D is 0 1 1, and then again 0 1 1, 0 1 1, 0 1 1. Okay, replace A by 0 0 0, B by 0 0 1, C by 0 1 0, D by 0 1 1, E by 1 0 0. Okay, now this table we are going to represent in this method. So that A is replaced by 0 0, B is replaced by 0 0 1, this is C, this is D, and this is A, right? So like that you can write down, this is C and this is A. So this is a reduced state table with a binary assignment 1. You can form the table like this for gray code, or you can write for one shot. You can do it. Therefore, the binary form of the state table is used to derive the next table and output. So the capacity of the combinational circuit, the complexity of the combination circuit depends on the binary state assignment chosen. Okay, some binary state assignment will leads to larger complexity, and some type of assignment will leads to simpler Boolean expressions. Okay, so that's it about the state reduction and assignment. So the thing is, we need to reduce the number of states. Actually, the design or synthesis goes like this. Okay, so the customer will give you the set of specification. From the specification, you form the state diagram. Okay, from the state diagram, you form the state table. From the state table, reduce the number of states, because we want to save the money. Okay, industry always wants to save the money, and get more profit, and then reduce the number of states, and then from this assign the values, assign the binary values. So you can binary value in the sense you can use binary code or gray code or one hot or whatever you like it, binary code, and get the Boolean expressions, and then finally realize. Okay, these two things we'll discuss in the next lecture. Okay, up to this we have discussed. So we started with a customer, set of specifications will be given by customer, and then from this we form the state diagram, and from this we form the state table, and then reduce the states, and then reduce the binary counter, assign the binary code, and then get the Boolean expressions. From that you can realize. These last two steps we will discuss in the next lecture, how to design the circuit. Okay, so this circuit, this sequential circuit is the heart of your computer, your mobile phone, or any electronic circuits. Wherever you find, wherever you see some electronic gadgets, you will find this sequential circuits. Even take a very simple automobile, for example, take your scooty or any scooter or whatever it is. If you have some digital display, there you have sequential circuits. There is a combination, there is a counter. Okay, one counter starts to count the kilometer driven till now, and another one is to indicate speed, right, and another one is to indicate fuel level. This all are your sequential circuits. So sequential circuit is a combination of flip-flops and combinational circuits. So everywhere the circuit will come. So we will study this in the next lecture. Thank you very much. Let me stop here.